Still needs lab for this week. All right, I don't have your exams done. I'm sorry, I'll be done on Wednesday. Maybe good news for some of you, bad news for others. Any questions on any? Academic or administrative? Everybody good? Had a nice weekend? Enjoyed the temperature cycle over the weekend? All right, so we'll wrap up with some phaser analysis for an hour or so, and then we'll have a team assignment. And then we'll start different viewpoint on phaser analysis. So again, this is all review, but our phaser form, we look at something like voltage, and then some amplitudes and some angle. Amplitude. And sometimes we'll write it like that. They're equivalent. So amplitude and magnitude kind of synonymous in this case. If you haven't seen this form before, and I think I've used it, so you should have, but two vertical brackets means magnitude. Take the magnitude of something. If it's just a real number, it's very easy. If it's a complex number, you use Pythagoras and find it. And then there's phase. The thing to remember, there's always an implied omega, which is our radial length. And so here's our phasor form, and then we can very readily translate that to time domain form. Bless you. With again some amplitude, same amplitude. And I tend to use cosine. You can use sine, it doesn't matter. Omega t plus b. As long as you're consistent. So if you use sine, always use sine. If you use cosine, always use cosine. So these are the same signals, just written a different way. And again, I know I've mentioned this a lot, but this is measurable. So that's what you get on your discovery board. This is mathematical. And measurable is always real. So this is clearly real, and this has a complex form. And we didn't write it here, but we could V equals V naught e to the J angle V. Same thing. So it has a complex form using Euler's law. And we walked back and forth, and we did that a lot last week. And we looked at KVL, KCL, mesh analysis, at least as far as setting things up, and node analysis. And we went through those problems, and assuming your calculator can do it, you can certainly do it on MATLAB or something like that, but use Wolfram Alpha, I don't care. If it's a matrix form, in the homework, find a tool that will solve the matrix for you. Unless you're really die-hard, ambitious, gotta do it myself kind of person, I would not do reduced row echelon with complex matrices. You can, I mean, feel free. It works. Probably take you a couple hours to do a 4x4, but time well spent. But MATLAB, and if you don't have MATLAB on your computer, you really should get it installed because you'll need it in other classes at some point. Or I guess someone said Wolfram Alpha. Speaking of calculators, something I should have said right at the start, I have apparently a fairly expensive calculator in my office that is not mine. Is yours? Yeah. Okay. That's a solved problem. While I'm certainly happy to take an expensive calculator, I probably wouldn't figure out how to use it. So the best I can do is put it on eBay. So I'd really rather return it to the owner before I gave it to the lost and found. All right. So stop by after class. Make sure you get it. So other things we haven't looked at for a little while, for a long while. Is a circuit with something like this. And I'll write it a little bit more arbitrarily. This is on the front page of the handout. this was our grid circuit. And we looked at this early on when we were considering how our voltmeter worked. And so, well, we also in the lab have an RLC meter, which is designed to tell us resistance, inductance, and capacitance. Well, with that in mind, if we think about this, what we want, again, we have a balanced bridge. When V bridge equals 0, nothing's changed. So it's balanced when there's no current through that resistor. And we can go back and do the same type of arguments we did several weeks ago. Call that V left and call that V right. And if it's balanced, that implies VL equals VR. Well, if we think about this a little bit, these are now sinusoidal signals, AC steady state signals. And we can rewrite this then as VL naught cosine omega t plus phi L equals VR naught cosine omega t plus phi right, VR. Well, thinking about that, how many variables or how many parameters do we have to relate here? I mean, the omegas are the same, but we have an amplitude that must be consistent and a phase that must be consistent. So when we consider no current going through here, well, these better have the same amplitudes and the same phase. And we can kind of prove that to ourselves a little bit. We step aside for a moment and consider a circuit. A simple circuit. So we have V1 and V2. And say V1 equals some V naught cosine omega t. And V2 equals V naught cosine omega t plus b. Well, we can look at the extreme case. If b is 0, and we want to be careful here for a moment, phi equals 0, these two are in phase. But what does that mean to be in phase? So I've drawn this with a little squiggly line for getting our normal polarities. When we define this as 0, we want to say at t equals 0, polarity. We need a reference when we think about this. At t equals 0, then V1 equals V naught volts, and V2 equals V naught volts. But in what direction? And so we do need to be a little bit careful. We haven't really used polarity, but we need a reference polarity when we talk about phase. And that matters here as well. So, well, at t equals 0, we have V naught at t equals 0, and then V naught at t equals 0. Thinking about that, what does that mean? Well, that's our defined polarity at t equals 0. If this is the case, what can we say about the voltage going through our resistor as a function of time? 0. This is oscillating, right? It's going to be 0. This is oscillating like this. This is oscillating like this, repeating, of course. And if we consider these nodes, and we throw a little ground in here, we haven't done that usually. Or not for a while, but, well, the voltage across this resistor is the voltage there, minus the voltage there. Both these are constrained nodes. We haven't used that terminology for a while, but if this is ground, this is V1, this is V2, and we can plot those as a function of time, of course. There's V1, and because they're in phase, because of our defined polarity at t equals 0, they're overlaying each other. And so there's V1, comma V2, and our voltage across our R, VR, V1 minus V2 equals 0. And we can trace that as a function of time. Well, let's think about this with our other situation. Maybe our polarity on V2 is reversed. Same amplitude, but if our circuit looks like this, give myself a little bit more room. So we still have plus minus V naught at t equals 0. And now we have minus plus V naught at t equals 0. Well, in this case, what's the voltage across our resistor as a function of time? Well, if we plot these out, is anybody still drawing? If we plot these out, once again we have a nice cosine signal, or sine if you prefer. And I've been drawing it starting at 0, but remember this is AC steady state. It doesn't exist for t less than 0. There's V1. Well, based on our polarity, here's V2. There's V2. They have the same amplitude. They're both oscillating between the same limits, but they're 180 degrees out of phase. And so what does VR wind up being? What does VR wind up being? V1 minus V2 is 2V naught minus 2V naught. Again, not drawing the scale, of course. But, so, same amplitude does not guarantee a balanced bridge, going back to the original discussion. We need to make sure that both our amplitude and our phase are the same in the left and right side. Everybody okay with this? Is it clear? With that in mind, if we think about this, if Z1 is some resistor, R1, this is some resistor, R3, and this is some unknown impedance, which means there's a Z real plus a J, Z imaginary. Well, we have an amplitude and we have a phase. What can Z2 be? There's more than one choice, but in concept, what does Z2 have to be? A capacitor. It can be a capacitor, but we need two things to vary. So our amplitude and our phase are going to depend on two things, both the real and the imaginary part. So Z2 has to be complex as well. So Z2 can be an R and a C, or an R and an L. And you tune them both. This is really the one that you use. Inductors are more problematic than capacitors. But you could do them. You could use them both. So you tune both components to find Z. Define what the value of our unknown impedance is. Now, for us, we're really just looking at the three basics, but this could be complex as well. So normally, when I use that component, when I use that device, I'm really just looking at inductors and capacitors. If I'm going to measure the ohmmeter or a resistor, I'll use the ohmmeter itself. Anybody use the RLC meter? Just out of curiosity. Did you look at what it was telling you? It has a little bit of information for you. So you're just using, but you didn't read the full display. So there's something that tells you on the display, it tells you it operates at, I think, 1 kilohertz. And so the ohm meter has an, or the RLC, the bridge, has an operating frequency. And this matters a bit because if you start to get components where something you're trying to measure is either very small or very large, like we talked about last week, at 1 kilohertz, it won't measure it very well. Some of these RLC meters, the more expensive ones, are tunable for different frequency ranges, and the one we have may be as well. You may be able to tune it up to 1 megahertz, I don't remember. But so this matters. This is measuring at a given frequency. It's doing the best guess. But it has a limit on how accurate it is. So, coming back to this guy for a second. Well, ZL and ZR, they're going to be balanced when what is true? Well, what type of circuit is this if the bridge is balanced? Our favorite type of circuit. It's the left side if the bridge is balanced. And the right side is also a voltage divider. So we wind up with something that looks like Z2 over Z1 plus Z2 equals Z4 over Z4 plus Z3 when the bridge is balanced. And we can do some similar algebraic rearranging that we won't bother with today, but we wind up with something that winds up being either Z1 over Z2 equals Z3 over Z4, or vice versa. Doesn't matter. Both of those better hold because they're just the inverse of each other. But just by algebraic manipulation, we wind up with this relationship. So these ratios must hold, but these are now complex numbers. And so for a given Z unknown, well, we would find out if Z4 was a Z unknown, like we've been labeling it. We could do something along the lines of which is essentially what we did way back when we looked at bridge circuits. So it's just a little bit of quick algebra. So where Z3 could be our tuning components. And that's what, essentially, in a simplistic sense, kind of what we do. On that token, we can do the little problem we have in the homework assignment or in the handout. And there's 1K resistor. And I threw a little bit of a curveball in there, but it doesn't matter. 4 Henry inductor. That's an inductor. Is anybody registering today? No seniors coming up? Is it during class?
Yeah, 5:30.
Yeah, so don't be shy.
Okay.
So if you're registering today, or you have an early registration or whatever, yeah, go register. I don't want you to miss out on classes. Of course, those of you who are back there playing games, it's a different story. So, here's our circuit. And again, if we're going to use our operating frequency, omega equals 1,000 radians per second, just for convenience. Well, again, just like we did last week, we want to convert everything to Z's. ZL in this case, 4,000 J. For H, ZL equals J omega L. And then ZR in this case, ZR1 I suppose, 1K, 1,000. And here we have our effective Z3, or Z2. But we have a capacitor and a resistor. What can we do here? Well, those components are in series. Yeah. What's that?
This is supposed to be the circuit from the handout.
Isn't it?
Your inductor is, so you got 400s, it's 40s, and
I put it out as a copy for you. Oh. Yeah, it's supposed to be 4. Sorry. Yeah. I didn't pay attention. So for me, it's 4. So it's supposed to be 4. Otherwise, it would be 4J. Scale would be very different. Of course, we can still do the problem, but when you're looking at very different numbers, scales, it's a problem. So ZC plus ZR1. So components in series add, and we know ZC is 1 over J omega C. So that's R2 plus R2, and we can do again a little bit of math. Minus J 2000 plus 2000. And ours is the unknown. Nicely laid out there. So, what can we do to find this? Well, again, Z unknown has to be 4,000. Minus J 2000 plus 2000 all over 1,000. Then we wind up with left off a J. And there's our Z unknown. Just again, a little bit of phasor math or however you want to arrive there. And the question that can be asked that's a little bit more interesting is, what is our Z unknown? You already kind of see it in the circuit, something similar. How do we build that Z unknown? What does it have to be? Well, what's this component? So the real part always a resistor. Positive imaginary parts are what? Inductors. So positive means inductance. And how could we build that? There's an easy way and a slightly harder way, perhaps. How could we build that? The easy way, you can just read directly. And we have an inductor plus a resistor. What is that from a circuit point of view? We just did it on the left side, so what is it? Someone said it. You say it louder. How do I build J8000 plus 8000? Series, sure. So this can be an inductor in series with a resistor. 8,000, and then this would be 8 Henry. Based on our omega on the previous page. Does this work? Can I do this? Not with the same numbers, but can I build them out of 2 parallel components? Sure. I don't know what they are on the top of my head, but it's okay as well. No matter how you combine inductor and resistor in series, you will always have a positive real part. You always have a positive real part, and you have a positive imaginary part. It doesn't matter whether they're in series or in parallel. You'll always have a phasor form of the impedance that has a positive term. So one of the things we haven't written a lot of, but we can write ZU, is magnitude ZU, angle ZU. And in this case, our magnitude was 8,000 square root of 2, angle 45, or pi over 4 if you prefer. And so anytime an impedance has a positive angle, that means it's inductive. So if angle ZU greater than 0, inductive. On the other hand, if angle ZU less than 0, capacitive. And that's something worth having in your notes. So when we combine more complicated circuits, well, a network of inductors or capacitors by circuit reduction is going to have some equivalent impedance. And that equivalent impedance will have an angle, and it will be either finally inductive or capacitive. At least your circuit reduced part is. This is a little bit of a side note. Then we have a ZU that's something like minus 1,000 plus J 1,000. Can you do that? It's a trick question. Can you have negative resistance? Sure, sort of. How do you build a negative resistor with active? No, superconductor is just essentially zero resistance, not negative. Active component. So if you remember, Thevenin resistance could be negative when we went back to that. So if Thevenin resistance or Thevenin impedance can have a negative real part as well. So this would be dependent sources, equivalent impedance. Thevenin, whatever, type of thing. So, can't have negative resistance, but it's a lump sum line. You can't go by a negative resistor. We mentioned that before. On the same note here, if we think about inductive versus capacitive, I think about my angle here for this particular problem. Can this angle ever be larger than 90 degrees? So if my circuit is inductive, if I just write this as and so in the long run, eventually we can write Z combined, whatever that is. That's R plus J omega L. So the real part and the imaginary part, we can write this as R squared plus omega squared L squared to the 1/2, angle tangent minus 1, omega L over R. Right? Very symbolic. That works. Can that angle ever be larger than 90 degrees? Or in some sense, what's our limit here? So R is a real number for us, so real components. No Thevenin here. Which means R, well, I can write it up here, R greater than 0 and L greater than 0. How does this behave then as a function of omega? In the limit as omega goes to 0, what's my angle? Trigonometric memory for you. 0 degrees. And the limit as omega goes to infinity, what's my angle? Been a while for the inverse tangent? It's the inverse tangent of a very, very large number. 90. So what's our operating range if our impedance appears inductive? 0 to 90 degrees. So that adds another little caveat on the previous page. So I can write it again. Z inductive. I'm not saying it's inductor, it appears inductive. We can write phi Z inductive less than or equal to 90 degrees, greater than or equal to 0. So I suppose 0 is Probably should just write greater than 0 to be a little bit more rigorously correct. And we can say the same thing about capacitive. What is our limits on Z capacitive going to be? Well, we can do the same type of math, or we can just infer it from symmetry. What are our limits going to be? Negative 90. Or again, pi over 2, which is a better way of writing it. So these are things to notice. If our impedance is positive, has a positive angle, it's an inductive circuit. If it has a negative angle, it appears to be a capacitive circuit. All this comes back eventually to Ohm's law. So we have V equals IZ. That hasn't changed. And we can write this as V angle V naught. We've done this a couple times. I angle I naught times Z magnitude angle Z. With that in mind, what's the phase difference between the voltage and the current? So if we look at a given component, or set of components, it doesn't matter. What's the phase difference between the voltage and the current? We could rewrite this. V naught angle V naught over I naught angle I naught equals magnitude of Z, angle of Z. And this is an arbitrary Z. It could be a whole bunch of stuff. We circuit reduced it. Could be a single inductor, single capacitor, single resistor. What's the phase difference between the voltage and the current? Ultimately, remember, this goes to some cosine omega t plus angle V naught, and this goes to some cosine omega t plus angle I naught. Well, what's the phase difference between those two? What does it have to be? In a given component or set of components, what's the phase difference between the voltage and the current? Comes out of the phasor math right here. The angle of impedance. So whatever we look at, the phase difference between the voltage and the current is always the angle of impedance of the component. I'm going to write it out a little bit circuit-like. We just take an arbitrary component, Z1, which is some magnitude Z, angle Z. We measure current across that. Well, V equals some V naught cosine omega t plus, we'll write a phi V there. And then we have current going down. Some I, and I equals I naught cosine omega t plus phi I. But we know the relationships for both of these. What does this have to be? Well, Ohm's law applies. We can rewrite this as V naught over magnitude Z, whatever the magnitude of our given impedance is. When we just had the inductor and the resistor, it was omega squared L. Here was our magnitude for this guy, but we've done this a lot, so we can find the magnitude. And then cosine omega t plus phi v minus angle Z. And so that holds. Once we know the voltage, and if we know the impedance, we can get the current directly. So Ohm's law applies, but now with complex numbers. And that comes out of this expression here. You know, we can write it however we want. If you look at this, magnitude, 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 we already talked about manipulating phasors. Then our magnitudes of our voltage, current, and impedance obey Ohm's law. Essentially, that's what I did here. You can say magnitude of V naught equals magnitude of I naught, magnitude of Z. These are amplitudes, so that's a little bit redundant. But the magnitudes must hold. That was the impedance relationship that I just put up here. And then our angles. So we can write this out, Ohm's law again. Angle of V equals angle of I plus angle of Z. And if we want, we can box that up. I mean, it's not terribly important. We've done all this already, but there's our Ohm's law expressions in terms of impedance. That has to hold. And then we can translate it back to time domain form fairly readily. Worth noting, we've essentially done that, but we just spelled it out right here. Everybody okay with that? And these are just kind of concept discussions, things to be aware of, perhaps related to the concept questions on exams. Maybe, hint, hint, nod, nod, wink, wink. So, everybody okay with that question? Are we clear? So, a number of you asked me a question about problem 5 on the homework. Did everybody look at the homework? Problem 5. Anybody know what problem 5 was asked? It's an admittance problem. What's admittance? Very, very tricky concept. It'll take at least weeks to get it. Admittance equals 1 over impedance. So Z in ohms, impedance of course, what we've been using all along, and admittance in modes. And that's a true story. I'm serious. Also called Siemens. And it's true. And so admittance is a used circuit parameter. It is truly the inverse of the impedance. So, you know, if you want to box something up, there you go. Y is 1 over Z. Now, if we think about this a little bit, yeah, it seems a little bit silly, but it has its practical applications. And I'll show you kind of why in just a second here. If we think about resistors in series, well, we did the Z equivalent, or probably should just draw these as boxes, call them Z1, Z2, call that Z equivalent. And we know Z equivalent equals Z1 plus Z2. And likewise, we can look at components in parallel. And so we've kind of done this already last week when we talked about impedance. And we have the inverse relationship. And Z equivalent now equals 1 over Z1 plus 1 over Z2 to the minus 1. Well, if we think about this guy in particular, if we convert this to admittance, well, Y is 1 over Z. So we can rewrite this guy 1 over Z equivalent equals Y equivalent equals, you could really be a little silly about it, 1 over Z1 plus 1 over Z2 to the minus 1 to the minus 1. So we inverse the inverse. And I wrote that out a little bit funny. But, and 1 over Z1 is what? Y1 and Y2. It's the admittance of this guy and this guy. equals y1 plus y2. Y equivalent equals that. So, if we want to use the term, even though it's kind of goofy, if we have the admittances in parallel, what is our property? They add. What about admittances in series then? What are we going to wind up with over here? Well, then we're going to have our inverse relationship. But this is actually kind of useful. So this inverse relationship, we can certainly extend it. We've had to do it in a number of homework problems and tests and whatever. But if we have a parallel connection, all we have to do is add admittances. Why is that useful? There's a physical motivation here. Yeah, it's partly to do with the next unit. Anybody have a guess? Why has this become useful?
It's easier circuit reduction.
What's that?
It's general easier circuit reduction.
Yeah, but why? I mean, there's a motivation here. You have a guess?
No discontinuity.
Not so much that. It has to do with how things are built. Loads are typically connected in parallel. You don't really ever connect loads in series. I guess you could, but normally you don't. So load networks, a lot of distribution networks, the power distribution network, motors themselves, a lot of parallel connections. So, and partly, there's a mathematical motivation here. If you can do addition as opposed to inverse relationships, I personally prefer addition. Addition's nicer. In a lot of the network theory that was developed, or analysis that was developed, admittance matrices were analyzed, and now with the advent of computer computation for problem solving, it's much, much easier to develop admittance analysis matrices than it is to build impedance analysis matrices. So even though this is kind of the physical real thing, you know, a lot of analysis tools can break down much more simply in admittance, and then you can go back out and find out what you need by admittance at the end. Yeah? You sure? So, you know, this isn't just, you know, a silly thing. It has a practical application in terms of engineering analysis. Now, it doesn't mean you can go to the Radio Shack and buy an emitter. You know, you can buy devices that are impedances, resistors, capacitors, inductors, and then you have to take the inverse to find the admittance. And so, as kind of an example of a load network, and we'll see this type of network a lot in Unit 4 as well, I gave a problem that looks like this. This is in the handout as well. And for our purposes, you know, when we do this stuff by hand or do it on paper, yeah, there's really not much of a difference. You know, you find the admittance, you find the impedance. There's the same button pushing either way, but it's good to be aware of the process. Whereas if you kind of extrapolate the thought process to many, many components, you could perhaps see how it would be easier in one method or another. So, if we want to find the admittance looking in, y question mark, well, this winds up being a ZC, a ZR, and a ZL in this case, and so y is going to be 1 over ZC plus 1 over ZR plus 1 over ZL. Certainly, as part of this process, we do have to know what ZR, ZC, and ZL are, which means we need to know a frequency. If I say F equals 500 hertz, then ZC is what? No, we'll do it down here. V naught over R, question mark. Possible? That would just be Ohm's law. It's like the inductor and the capacitor don't exist. Is that possible? Is that possible? Sure. Under what conditions? Well, J omega L minus 1 over omega C equals 0. Well, that looks a little bit suspicious. Omega squared equals 1 over LC. It doesn't go away ever. And this is actually where the term resonant frequency comes into play. So we used that term before when we were looking at RLC circuits in our transient analysis. And this has more meaning here. Current is flowing in this case. If we think about this, current in the whole circuit, V naught over R, right? Current flowing left and right, oscillating back and forth. V naught is the amplitude, sinusoidal signal with the voltage varying up and down. So current is also oscillating back and forth. That means current going through the inductor, oscillating back and forth through the inductor, current oscillating back and forth through the capacitor. How is this physically possible? How is this physically possible? What's going on? So as the current goes back and forth in the capacitor, charges and discharges, right? It's absorbing and releasing energy. That's what capacitors do. Storing and discharging current. Storing energy, releasing energy. And that's what inductors do. Under this, when this is going on, what can we say about these two guys in an ideal sense? It's a little bit tricky concept, I think.
Equal and opposite.
They're equal and opposite. They're trading energy back and forth. So the capacitor is charging at the same rate, the inductor is discharging in some sense. And likewise, the capacitor is discharging at the same rate the inductor is charging. So they're storing energy, but they're trading it back and forth during cycles of the sinusoid. So essentially, you know, they have some energy, just giving it back and forth, and it's like they don't count. So all we see effectively is the resistor. So in this state, Z total equals R. At the resonant frequency, we will see the total resistance for this circuit is just R. In other words, ZL equals the complex conjugate of ZC. They're equal and opposite. They cancel each other out. We'll visit that a lot more. All right, coming up on time for a team assignment, it is about phasors. Before we start the team assignment, this has some bearing on the team assignment. So it's up in there. This looks very similar to the team assignment. Two sources. Out of phase. How would you solve the problem? Or maybe even have different frequencies. How would you solve the problem? Two sources out of phase. Different frequencies. What's that? You have phasors to the source if they're the same frequency, but if they were different frequencies, and your homework or your team assignment is not, but if they were different frequencies, how would you solve the problem? Define voltage or current or whatever through one of these components. Superposition. So superposition can be your friend. We haven't talked about that one yet, but everything we did in Unit 1 applies. So, and I think that's the last Unit 1 topic that we did mention. We talked about Thevenin resistance, Thevenin equivalence, impedances, Nash, KVL, KCL, all that fun stuff. We can apply everything we did in Unit 1. Superposition, turn off all the other sources, off for current sources and open, off for voltage sources and short, etc., etc.
All the fun stuff.
Fun stuff. All right. In this case, you can do the solution however you want. There is a little surprise in this problem. You're, of course, welcome to ask. You can have a team assignment without surprise.
That's the one where you like eliminate one? And then you eliminate
So if you're looking, the I1 side of the expression, you wind up with something that looks like this, right? So there's our circuit. And so this is ZC, this is ZR, this is ZL. And the question you're asked for is VL, right? Well, from a circuit reduction point of view, what can we say about the voltage across the inductor? It's the same as the voltage across the resistor, same as the voltage across the capacitor. So ZL, in some sense, equals Z total times I source, right? Does everybody agree? Where Z total is ZC in parallel with ZR in parallel with ZL. And that's some complex number. I don't know what it is on top of my head. But is everybody comfortable in getting this? This winds up being, you know, you can calculate it out, Z total real plus J Z total imaginary. Is everybody good with that? Now this also equals Z total magnitude angle Z total in phasor form. So what's VL? VL is Z total magnitude angle Z total times I source magnitude, which we know is 0.015. Angle I source, and I don't remember what this was, but this winds up being magnitude Z total times magnitude I source, that means 0.015, times angle Z total plus angle I source. And this was pi over 4, 45 degrees, whatever you want. And so once you found the equivalent impedance, if you're doing it this way, then you multiply the magnitude of Z total times the magnitude of IS to find the amplitude of the voltage. You add the phases to find the angle of the voltage. And that's it. Does that answer your question, or is there the next step the one that bothers you?
No, it was converting I source to, right now you have Z total equals the three impedances in parallel equals Z total real plus J Z total.
Right. Oh, well that comes, so that's what we did in the lab last week, or I did it in class a couple times. So if I source equals 0.015 angle 45 degrees, in rectangular form, this is 0.015 times cosine 45 plus J sine 45. That comes out of Euler's law, essentially. I source is some I naught, angle I naught. We can write that as I naught e to the j angle I naught. We can apply Euler's law to that complex exponential. I naught cosine angle I naught plus j sine angle I naught. So that's walking the other way, going back and forth. So that's going from the complex form, the phasor form, to the trigonometric form, or vice versa for the tangent form. So if we want to write this as I real plus j I imaginary, I guess. This is I naught, cosine angle I naught, and this is I naught sine angle I naught. Right? Does that answer your question? This is in a table in the last lab, so maybe grabbing the last lab for your crib sheet, for 3 weeks from now or whatever it is. Or copying that or something. It's probably a good thing. Actually, just as kind of a aside, how many people have never seen complex numbers before this class? Really? No one? I mean, where you actually solve stuff with them, or you just heard of it? So everybody's used complex numbers before this class? In differential equations, you use complex numbers? Okay. I was just curious because historically, actually, about half the class raised their hand. Curious about how the backgrounds change and whatnot. Okay. Any other, are we good? So any other questions on this? I mean, I'm happy to address questions, but you got to ask. Yeah.
Can you check graphically as well as the conversion rather than all trigonometry stuff? I guess it equals out to the same thing. But if you like graph it like real imaginary axes.
Yeah, I suppose. So you mean like vector solutions?
Yeah.
Yeah, I guess that works. I never really thought about it, but yeah, of course it's got it. So the question was, can you use vector solutions? So if you have like a phasor form that looks like that and a phasor form that looks like that, can you do, what was it called, a quadrilateral rule or something like that? Can you do this and then find this? Yeah. Essentially that's adding the rectangular. That's, in order to get this, you have to convert these to rectangular form and add them, so effectively it's the same thing. Slightly different presentation. Yeah, I never thought about that, but it's a good point. Any other questions? Okay, so let's go back to our old friend, but we're going to look at it in a slightly different manner. So let's go to our old friend, the RC circuit. And so if we look at this guy, we can ask again, what's VC? Well, VC is ZC over R plus ZC, or ZR, the more general, ZC times V source of course, R, and then C. And so if we look at this, well, one of the things we did in the last class was V source of S equals 1 over SC, R plus 1 over SC times V source of S. We did a little division. We called this V out of S over V in of S equals something called the transfer function, which is the ratio of the output to the input. In this case, 1 over SC, and if I do a little bit of rearranging, I can write this as 1 over RC, S plus 1 over RC. And again, we did this in Unit 2, so there's nothing new, other than we made our lives a little bit better because we no longer have initial condition terms to worry about. but this is the ratio of the response. The transfer function is the ratio between the output and the input. In the S domain, in AC steady state, we know S goes to J omega. So we can find our transfer function. Once we have our transfer function, we did this last class, we can plug in J omega and then evaluate for a variety of omegas. So same thing we just did in that problem. You had a given frequency. Well, if we wanted to look at multiple frequencies, we'd want to find our transfer function and then just plug in numbers using a calculator tool or something like that, so we didn't have to work very hard. Well, looking at this, we can write h of j omega for this problem equals 1 over RC j omega plus 1 over RC. Well, looking at it in that form, this is complex form. R and C are numbers. Omega is a radial frequency, so it's another number. And so we can look and characterize. We have the magnitude of the transfer function is the magnitude of the output over the magnitude of the input. That holds. That would be the amplitude of the sinusoidal signal. So the amplitude of V out over the amplitude of V in is related to the magnitude of the transfer function for some frequency, of course, for a given radial frequency. You have to do a little bit of math there, of course, and we're starting to get to be experts at doing phasor math or whatever the case may be. But the magnitude of the transfer function. Is related to the amplitude ratios. So a magnitude transfer function related to the amplitude ratio. That has to be the case. Likewise, we can say the angle of the transfer function equals the angle of V out minus the angle of V in. Now, I already brought this up once before, but just to revisit it for a second. If the angle of the output and the angle of the input are the same, what must be true about the angle of the transfer function? Well, if angle V out equals angle V in, what's the right side? So what does the angle of the transfer function have to be? And if that's true, if the angle of the transfer function is 0, from a circuit point of view, what must be true? Looking at this, there's only one particular case where this is purely, or where that has an angle of 0. It's when omega goes to 0. So if the angle of the transfer function is 0, that means the transfer function looks, in this case, purely real. And the only thing we have purely real is resistors. So something to pay attention to, and that goes back to what I said about current and voltage in a component. If they're in phase, then the component is resistive. These are only in phase for DC analysis. So, looking at this, we're going to take our magnitude one step further. So we can take this magnitude expression and we're going to take 20 log of the magnitude of h of j omega. And this has specific meaning, specific units. Does anybody remember? I think we saw it in physics too. Anybody remember what that is? You didn't see it? This is decibels. decimals? No? I don't know. I never taught physics too, so. 20 log of the transfer function winds up having units decimals. And we'll look at this quite a bit. So, looking at our little circuit here, our RC circuit, we can construct a table. Let's say omega. Look at the magnitude of h of j omega. And then 20 log of the magnitude of h of j omega. And essentially, let's give ourselves some components. That's 100, 10 to the minus 6. And so let's look at omega equals 100. So 100 radians per second, of course. And to give myself a little bit of room, well, in this case, h of j omega, then I hope we agree, winds up being 10 to the 4 over 100j plus 10 to the 4. 1 over RC was 10 to the 2 over 10 to the minus 6. I had written the transfer function on a previous page, so 1 over RC over j omega plus 1 over RC. Well, we can look at the magnitude of this, and we can actually do this somewhat by observation. Magnitude of h of j omega. What's the magnitude of the numerator? What is the magnitude of the numerator? Yeah, 10 to the 4, just to make sure we all agree. So the magnitude of the numerator is 10 to the 4. You can write magnitude bars around it if you want. What's the magnitude of the denominator? You don't have to be precise here. It's about 10 to the 4. It's a little bit less than 10 to the 4. So, draw a little tiny less than sign, 10 to the 4. And so it winds up being about 0.9999, the 4 nines.
It's a little greater.
A little greater, sorry. That's right. Let's say it correctly, of course. A little bit greater there. And so this is 0.999, lots of nines. Well, then we can go and say 20 log. Well, what's log of 1? So this is pretty close to 0. About 0.00043. So this winds up being 0.00043. In this particular case, what can I say about the voltage of the output relative to the voltage of the input? They're about the same. So, looking at this, when the transfer function is about, when magnitude of the transfer function is approximately 1, V out magnitude is approximately V in magnitude. And so the output equals the input, approximately. And the phase will be close as well. And so that's what we see here. Likewise, our dB value is about 0. Then I'll have a lot more bearing. Don't really have a lot of time here. I need 10 more minutes. You guys willing to stay? All right, we'll pick this up on Monday. Or Thursday, whatever it is.
Yeah.
What's that?
Monday. Bring back Monday.
You got it.
I'll be here Thursday. You can do what you want.